Hello everyone. In this video we will understand in PUCCH format 1 how the data is being transmitted, means how HARC and SR are encoded. We will also understand how the UE multiplexing is done and how many UEs can be multiplexed. We will also understand how the receiver can be designed. Okay, so let's go over them one by one. Okay, as we have seen in the previous video, if it is 1 bit of information, we do BPSK modulation. If it is 2 bit of information, we do QPSK modulation. Okay, and the modulated data is multiplied with the ZC sequence and then transmitted. Okay, now let's see how it is mapped to the resources. So a UE is always allocated with two different resources, one for HARC, okay, and one for SR. So basically a UE always has two PRBs, okay, one for HARC, these resources here, and another resources for SR. Okay, they can be placed at two different locations in the frequency. Okay. So when UE needs to send 1 bit of HARC, okay, then it will do the BPSK modulation, okay, and it will send it on the HARC resources. Okay, that means these are the HARC resources. Okay, when it is 2 bit of HARC, then also the same process, it will do QPSK modulation and it will send on HARC resources again. So if it is 1 bit HARC or 2 bit HARC. Okay. If there are SR resources, okay, if it is UE is supposed to send SR, then it will do BPSK. So basically when the SR is positive, it will always modulate 0 and it will send it on the SR resources. That means it will send here, okay, if SR is positive. Okay, when it is 1 bit of HARC plus SR, so UE is supposed to send HARC and SR on the same slot. In that case, it will send 1 bit HARC on SR resources. Okay, in that case, if SR is positive, then it will send it on SR resources. Okay, the 1 bit HARC is sent here. So 1 bit based on the ACK and NAC, it will do the modulation, BPSK modulation, and it will send on SR resources if SR is positive. If SR is negative, then this is sent on HARC resources. The same apply for 2 bit HARC and SR is positive. In this case also, if SR is positive, then we send it on the SR resources, the 2 bit HARC, and if it is negative, then we send on the HARC resources. Okay. So for G node B detecting 1 bit HARC and 2 bit HARC without SR, it's simple. It will go to the HARC resources, that PRB, and it will identify if there is a HARC, ACK or NAC. Okay. If U is scheduled to send HARC and SR both, then G node B will look at HARC and SR resources and it will see where the data is transmitted. If it is transmitted to the HARC location, then U is not sending any SR. If it is sent on the SR location, then G node B will think that U is requesting SR and also it has sent HARC ACK. Okay, so this is how the data is encoded. Now let's understand UE multiplexing. Okay, in the previous video we have seen the orthogonal sequences WM. Okay, it depends on the number of symbols. If there is one symbol, then only one sequence. If there are two symbols, two data symbols. So basically these are PUCCH data symbols. If there are 7 symbols, then 7 orthogonal sequences are there. Okay, so this is called orthogonal code cover, OCC sequences. The other thing that we have seen is cyclic shift. Cyclic shift, okay, where we have seen that M0 is the initial shift, okay, that is also used to multiplex different UEs. So now we have two different things. One is the orthogonal covered core, another is the cyclic shift, and both can be used to multiplex different UEs. Okay, so let's take an example and understand how the UE multiplexing can be done. Let's consider an example of 4 UEs. Let's say there are 4 UEs, okay, where we want to do 2 UEs are multiplexed using cyclic shift and 2 UEs are multiplexed. These two are multiplexed using OCC. Okay, these two also multiplexed using cyclic shift. Okay, so this way we will cover all the different combinations, and the same rule is applied when we are multiplexing more UEs more than 4 or less than 4. Okay, so let's assume PUCCH is scheduled with 4 symbols. Out of 4, 2 are DMRS and 2 are for data. Okay, let's take a scenario here. Okay, so let's assume that for these UEs we have fixed, or we have signaled M0, the initial shift, as, let's say, 0 and M0 as 6. Okay, since we know for M0 is 0 and 6, for this cyclic shift both the ZC sequences generated are uncorrelated. Okay, this concept we have used in format 0 as well. So for different cyclic shift, the generated signal is uncorrelated. Okay, and same here. So I will map them UE1, UE2, UE3 and UE4. And these UE3 and 4 are also signaled with M0 as 0 and M0 as 6. Okay. Now for 2 symbols, as you see here, the orthogonal sequence is 0 0 and 0 1 for 2 symbols. So if you do e to the power z 2 pi phi m by 2, then what we'll get is, for 0 and 0, or Wm will be 1 1. Okay, and for 0 and 1, Wm will be 1 and minus 1. Okay, so let's say we have signaled, to make it orthogonal, we have signaled these UE1 and 2 with 1 1. Okay, the Wm that is used, so basically the index that is signaled is I is equal to 0. Okay, so these two UE has I is equal to 0 and I is equal to 0. Okay, where these two UEs 3 and 4, they have Wm as 1 minus 1. So I is signaled as 1 and 1. Okay, so this is how these two group. So here, as you see, UE1 and UE2, their generated signal is uncorrelated. UE3 and UE4, these signal is also uncorrelated with each other. Okay, and UE1 and 2 and UE3 and 4 are in different orthogonal cover code. Okay, so that way UE1 and 3 are also orthogonal, UE2 and 3 are also orthogonal, UE1 and 4 are also orthogonal, UE2 and 4 are also orthogonal. The generated sequence is orthogonal with each other. Okay, this way we provide the orthogonality, and also uncorrelated signals. Okay, so if you look at this way, if you want to multiplex more UEs, one is to provide more cyclic shift. As we know, cyclic shift alpha can take 12 values, 0 to 11. Okay, so it's 2 pi 0 to 11 by 12. So based on different alphas, 12 different uncorrelated sequences can be generated. And if you use 7 symbols of data, that means 14 PUC symbols for PUCCH. Okay, out of that 7 data, we can generate 7 orthogonal cover code. And for each orthogonal cover code, there are 12 sequences. So in total, we can have 84 UEs multiplexed. Ideally, we can multiplex 84 UEs. Now, based on different channel conditions and all, the actual UE that we multiplex may be quite less. Okay, if you want to keep all UEs on different orthogonal cover code, then we can provide the same cyclic shift alpha, and we can multiplex 7 UEs where all of them are orthogonal. If you want to keep same OCC and vary alpha, then we can have 12 different cyclic shifts, and we can multiplex 12 UEs sending uncorrelated sequences. Okay. So taking this example forward, so the G node B will receive data of all 4 UEs in this allocation. Okay, this allocation will have data summed up of all 4 UEs, UE1 plus UE2 plus UE3 and UE4. Now G node we need to utilize first the DMRS signals, OCC sequence and cyclic shift. Okay, it needs to utilize all 3, okay, to decode and find out what was transmitted from each UE, okay, on this received data. Okay, so let's understand how the receiver works. Okay, so let's go step by step and see what happened at the transmitter. Okay, so UE, when it generated the sequence, it picks the root sequence first. It picks a U. Okay, then we pick M naught cyclic shift. We generate ZC sequence. That's what we have done in the transmitter. Okay, then on top of that we apply OCC, orthogonal cover code. Okay, and then we do IFFT CPN transmit. Okay, so at the receiver, so this is done by all 4 UEs, where UEs have picked up different M naught. Here we have picked 0 and 6, and you have also picked up different OCC, I is equal to 0 and I is equal to 1. Okay, now at the G node B, it has to do reverse of it. Okay, so it will receive the data, that means that PRB. Okay, this PRB has 4 symbols, 2 DMRS, 2 data. Okay, now on the data, first we need to estimate the channel. Estimate the channel. So here I am just giving the idea of how the receiver can be designed, since these are proprietary and every vendor can implement differently and may implement very complex algorithms, okay, for a better receiver design. But here we will discuss the idea of the receiver, how the receiver can be implemented. So we need to estimate the channel. So first we'll use the DMRS. Okay, we'll use DMRS. Okay, we know that what OCC was applied. So on the DMRS we have 2 symbols. Okay, I will call them D1 and D2. Okay, and we will first remove the OCC. Remove OCC. Okay, so basically you multiply the conjugate of it and then remove the OCC. Okay, so once you remove the OCC, we will get 2 channels. H1. I will call them H1 and H2. Okay, H1 is for one group. We have seen there are two groups. Okay, this I will say group 1, group 2. Group 1 is for UE1 and 2. Okay, this is for UE1 and 2. This is UE3 and UE4. Okay, now this is the channel that we have H1 and H2. Okay, after removing those, so basically we multiply with the orthogonal cover code one by one, and we separate the H1 and H2 from the received DMRS. Okay, that is nothing but D1 and D2, the received signal on both the symbols. Okay, once we have H1 and H2, okay, then we need to separate it for each UE. Here from H1 we need to find the channel estimate for H1 UE1 and 2. From H2 we need to find it for UE3 and 4. Okay, now we know the ZC sequence and the cyclic shift that is given to the UE. So that means we know the root sequence U, we know the cyclic shift that is given to the UEs, and we also know NCS. Okay, so we will generate the base ZC sequence. We will generate the base ZC sequence. Okay, and we will multiply with the conjugate of it. Okay, to each of them. Okay, so by multiplying the conjugate of it, since it's a both UE1 and 2 have sent uncorrelated DMRS. Okay, so from H1 we will get channel of UE1 and UE2. Okay, and similarly from H2 we will get the channel for UE1 and UE3 and UE4. So this is how we will separate the channel. Now we have the channel between each UE and the base station. So basically we have estimated this channel here from UE1 and base station, UE2 and base station, UE3 and base station, and UE4 and base station. Okay, this we have estimated. Okay, now the goal is to get the data. Okay, now on the data also we can first remove the OCC, the same process. Okay, we can multiply with the ZC sequence. Okay, since we know M0, since we know the DMRS and data are processed in the same way and the same sequence have been generated, we know M0, NCS and root sequence. Okay, and this is how we separate the data. Separate the data. Okay, once we separate the data, okay, and we also know the DMRS for each UE. Okay, with this DMRS we will equalize. Basically we will derotate the data using the DMRS. We will remove the channel effect. Okay, that means equalization. We will remove the channel. Okay, and then we will get the symbols. Okay, so we will detect one of these four, like either this or this, and then based on this we will find out what was transmitted. We will get the TX data. Okay, and this is how the receiver works. Here one of the strong assumption is in the channel estimates over here on the applying the ZC sequence to separate the channels for UE1, 2 and 3, 4 is that we assume the channel remains constant across the PRB. Constant channel across PRB. Okay, so we have assumed that this H remains constant across the PRB to make sure that the ZC sequence remains uncorrelated to get the channel. Okay, so we can even average the DMRS, average the channel estimates, and then we can find out channel estimates for UE1, 2 and 3, 4. Okay, so when we are multiplexing the UEs, okay, it's a We need to decide whether we want to multiplex them using different OCC or we want to multiplex them with different cyclic shift. Okay, both are two different methods and may give two different results. So this is all about the PUCCH format 1 receiver. Thank you.